that Z-bar group in 2010. They seem to be making a habit out of this.
Okay, so
But it's interesting.
Also, actually, yesterday, Arvind was mentioning that he had this paper on simple. Were you on that paper?
But Emma was.
Okay, because I bid on it
yeah,
first.
I kind of figured. I mean,
Oh, well, you're not conflicted with it.
Yeah, I'm not.
Oh, that's why you're asking me.
Yeah. I bid on it, and then he talked about it, so I like read the abstract, and then we talked about it.
Well, someone has to review those papers, so I don't think you have any excuse to get out of it.
oh yeah, otherwise it takes forever to the thing to load the MTAG or whatever. Yeah, I know what you're talking about. Yeah, that's actually a good. Yeah, I should do that. That's a good call actually.
Okay, so let's get started for today. The main topic for today's lecture is going to be on advanced topics in imitation learning, as well as safety in imitation learning and reinforcement learning. So there's three main things that I'll talk about today. The first is when we're imitating humans, how do we handle domain shift? I'll talk a little bit about that problem in a minute. Safety while learning, so we want our agents to be safe and not hurt themselves or hurt others while they're learning, as well as improving imitation learning from experts methods that we covered in a few weeks ago. And note again, like the previous lecture, this is an open area of research, and so a lot of the things that will be covered today are potential solutions to these problems, but it's very much an open area, and a lot of the papers I'll be covering came out in the past year or two, and so keep that in mind. But next lecture, there'll be a lot more theory, a lot more technical content on inverse reinforcement learning. Okay, so let's get started. So the first topic is going to be on imitating humans and handling domain shift, which is that in the previous lecture, when we talked about imitation learning, the applications that we discussed were mostly for autonomous driving or for drones, so essentially for mobile robotics. And when you're providing demonstrations for these sorts of vehicles, it's quite easy to just control it as if the robot would control it. For example, you could just drive the car, or you can remote control the drone, and those are fairly easy ways to control the system, but and very similar to how the actual computer would control the system. But if the system is a robotic arm or a humanoid robot, it can be much harder to provide demonstrations for because the system has a lot more degrees of freedom, and trying to do some sort of remote control operation doesn't really make a lot of sense. So a question for you all: how would you what ideas do you have for how you would provide demonstrations to a robotic arm or to a humanoid robot? Any thoughts?
Can you just physically move the arm?
Yeah. So one option is to physically move the arm through the motions, and that's called kinesthetic teaching. And I'll show some videos of that in a second. Any other ideas?
Could you just use video data, right? If you move a lot and take a video of it.
A video of what?
I guess. Well, yeah. I guess maybe it wouldn't work too well.
Yeah. Okay. So this is a pretty challenging problem. How would you actually provide demonstrations for these sorts of systems? And so one way that you can do it is, just like mentioned before, is through kinesthetic teaching. So this is a video of Katharina Muehling, who is currently at CMU, and she's guiding the arm through the motions of playing ping pong. And she makes this look very, very easy, but generally moving the arm like this can be actually quite challenging, especially for people that aren't researchers and aren't people that do this on a regular basis. So if you actually want to have an average human being teach a robot how to do something through this sort of method, it can be quite challenging. And then, so another way to do this is through teleoperation. This is basically the same as kinesthetic teaching, except in this case, there's another arm that the human is controlling, and the other arm is matching what that other arm, matching what the arm that the human is controlling is doing. And again, this is a video of Peter Pastor, and again, he's making this look quite easy to do, but in practice, this is quite challenging. He has a lot of experience in these sorts of demonstrations. Okay.
What's so challenging about it?
It's not intuitive. So you have to, especially in this case, like the robot arm, you have to kind of figure out how the robot arm is moving and what's its degrees of freedom are. The way to do the task isn't necessarily the same way that you would do the task yourself, because its arms are different lengths. It has different joints. Yeah, once you kind of get the hang of it and kind of understand how the robot works, it's a little bit easier. But it definitely takes a lot of practice to make a smooth and nice demonstration. And as you might imagine, if you had a humanoid robot and you're trying to teach a humanoid robot how to walk, something like that might be even more challenging. And the third method that I'd like to mention is VR teleoperation, which is, in this case, this is a prototype built by Zoe McCarthy here, who is teleoperating the robot by, she has two fake gripper hands that she's holding. And there is a face-based system that's tracking the position of the grippers that she's holding, and then mapping those onto to the pose of the actual robot, which is shown in the background. And then she's wearing a VR headset, and that VR headset is projecting what the robot sees while she's performing the actions. So here's a part of the video, so you can see that this is an early prototype. Her version right now is much more sophisticated than this. But you can see that she's able to kind of mess around with the objects through kind of this first-person thing. And this is what, in her early version of the prototype, this is what she's actually seeing in the VR headset. And I've talked to her a little bit about this. And again, so this could be one very interesting way to actually control robots, because you can actually get the first-person view of what the robot is seeing. But I've also, from what I've heard from her, that it is also something that you have to really get the hang of. And I know that undergrads that she's working with that are just starting to figure out how to record demonstrations on this system, she says, from her perspective, because she's done this for many, many times and she designed the system, she has a very good idea of how it works, and she's very good at giving demonstrations, and people that are just starting off need more training to be able to get good demonstrations. Okay, so kind of an answer to the question that I posed before is most popularly kinesthetic teaching and teleoperation are two of the most popular ways to try and give demonstrations for these systems. And in this lecture, I'm going to cover ways that we can give demonstrations beyond these two methods and be able to give more natural demonstrations and basically, move beyond these sorts of things. And the main challenge that comes up when you try to move beyond kinesthetic teaching is that if a human is doing the task and a robot is watching the human doing the task and is trying to imitate that, there's going to be a domain shift problem. And what this is that first, humans can do things that robots can't do, and vice versa. So if a robot is watching a human do a task, a robot shouldn't necessarily do it in the same way that the human does it. Just generally, the constraints of how the robot is doing the task is very different from the constraints that a human is doing the task. It's likely that a robot might be able to do it more efficiently, depending on its degrees of freedom. And the second reason is that humans look different from robots. So if a robot is watching a demonstration of a human do the task, even if it's from the first person, from the human's perspective, the human hand is going to look different from the robot hand. And it needs to figure out that it's OK that it doesn't have the same hand as a human when it's trying to perform the task. And the last point to note is that when you are using expressive function approximation methods like neural networks, like deep neural networks, this domain shift becomes more of an issue because the the neural network will pay attention to what the human looks like and how the human is doing things. And whereas with linear functions, you might just underfit, and you don't have this problem as much. So in the next like 15 to 20 minutes, I'll cover different methods for trying to handle this domain shift problem and get demonstrations from humans without having this be a problem. Okay, so the first method that I'll talk about is actually building off of the last method that I talked about last lecture. And so recall last time we talked about how we can use inverse models to learn how to do tasks, where the inverse model is fed in an image before the initial image as well as the goal image, and then it's trying to predict the action of how you get from that first image to that last image. And the limitation is that you can't really plan with this inverse model. So if you're given, this is the paper that I'll cover today, and the way that they tried to use this at test time is it would be given the current image and the goal image. It would try to greedily predict how to get to that goal image, even if it wasn't achievable in a single action. And so you can imagine, what if the robot was given an initial image of an untied rope and a final image of a tied rope? There's definitely no single action that can get you from an untied rope to a tied rope. And so this sort of approach isn't going to work because it can't plan actions. It can't plan a sequence of actions to try and get to the tied rope. And so what this new paper is what this follow-up paper is trying to address is, can we get sub-goals for how to get from the initial state to the last state from a human demonstration? Okay, so what they do is similar to the previous paper where they were trying to poke things. This time they had a rope, and they had the robot collect a lot of data of picking up the rope and moving it to a new place. So here's a video of some of the data collection, and you can see that one end of the rope is fixed, and it's using a Connect to get images of the setup. And it's randomly picking up a place on the rope and moving it to a new location. And this is in order to train the inverse model to be able to predict, given a first image and a second image, what is the action, what is the place where the robot picked up the rope and the place where it placed the rope in order to achieve the second image from the first image. And they obtained quite a lot of data in order to train this inverse model. And then at test time, when they were trying to actually achieve a much more complex and much more complex goal, and a goal that requires multiple time steps, what they did is they had a human provide intermediate steps, provide intermediate images of intermediate goals. So for example, every time you see Ashvin here pressing on the keyboard, he's having the record an image of the intermediate state of the rope. And then at each time step, the robot is trying to get from its current image to the next intermediate goal that was provided by the human. And you can see here, using these intermediate goals provided by the human, the robot is able to step-by-step move the rope into the configuration into the final configuration, which wouldn't work with the one-step model. And then here's one final video of another shape with the rope. And then here was one last one where it was trying to tie the rope using the learned inverse model. And so the robot is able to, using the sub-goals that the human provided, using those intermediate images, it was able to tie the rope. Yeah?
Like, to what extent is there like any generalization? Because this is so specific. Like, you move the rope in like very specific places, and it's literally just copying like what you're doing. So
yeah.
If you move the rope in like if you want it to move in any different way, is it going to be able to accomplish that?
Yeah. So I guess there's two kind of things here. The question was how much generalization is there? And how much can we expect from this sort of model? I think that last example of tying the rope, that was actually quite different from the data that it saw during data collection. And I'm not completely sure, but I think that...
Depends on like a pixel-wise distance between the images that you get out of this, right?
Yeah.
Like
the rope can be in a very similar configuration, but the actual difference between the pixels can be enormous.
I see.
If it's just like 2 centimeters to the left.
I see.
So it's rather specific, but
Okay.
it's sort of deceptively difficult.
Got it. Okay.
And I mean, the other thing to mention here is that all of the data was collected on like a green background and a red rope, and if you did try and move it into a different environment, it definitely wouldn't be able to handle that because it wasn't trained on that sort of data. So it needed to see much more diverse training data at training time in order to be able to generalize to more environments. Yeah.
Correct me if I'm wrong, but I think that the tying itself is kind of a trick here, right? Because you move the rope over the loose end, and then the robot is trained to move the loose end, so it picks it up and lifts it through the loop accidentally, right? It's not like actually, or in its mind, it's not tying it, right?
Yeah. So the question was, does the robot know that it's tying the rope? I guess.
I'm just saying that it kind of looks on to the question of generalizing these things. Because, I mean, you train it by moving parts of the rope.
Mm-hmm.
And I would say that the tying of the rope only really works because you put the loop on top of it. If you put something else that would sort of mismatch what you've shown it during training, it wouldn't really work.
Yeah. So I guess are you saying that if you wanted to do a task that wasn't just pick up the rope and put it somewhere else, it wouldn't be able to handle that?
The robot can't do anything else with that. So.
Yeah.
Yeah, I guess you're right.
You need a more complex action space in order to do more complex actions. Yeah.
I'm curious, when the human is moving parts of the rope, does the robot only get to see the final image, or like the sub-goal images, or does it also see where the human is placing his hand to lift the rope?
It only sees the images. So what the robot sees is this image in the top right. And so let's see if I can move it back a little bit. So for example, here's one of the, I guess in that example, it has the robot gripper in the, this is during robot executable. So in the top right shows the intermediate goals. And I guess that's only showing the final goal. But during the task, it sees the image without the human hand in the scene from the robot's perspective.
I think it's pretty impressive that it even knows like where to actually grab the rope to actually maneuver to the final step.
Yeah. I think it's pretty cool that their inverse model is able to figure out how to pick up the rope and how to place the rope, only seeing its current image and the goal image.
So and that inverse model was trained first before.
Yeah, the inverse model was just trained ahead of time using the data that was collected by the robot.
So I think that's the generalizability right there. Is coming from the inverse model.
Yeah, exactly.
Was the robot able to form this little loop itself? Is that just not shown in the video, or?
I think the initial loop that was just placed by the human, although Sergey might know. I wasn't involved in this paper, but Sergey was.
The draft is on archive, and it says sort of the success rate. I mean, it's not perfect. It's very far from perfect.
The initial
So
loop.
I think this one, in this video, the loop was made by hand first. It does make the loop itself, but like 40% of the time or something like that.
Okay, so kind of looking at this method at a glance, how does it handle domain shift? So kind of the first observation is that the human is removed from the scene. This isn't always a solution. First, often it might be hard to remove the human from the scene, especially if you want the robot to be able to see kind of a continuous action that the human is performing. For example, maybe if a human is pouring water from one cup to another, it's going to be hard to erase the human hand from the scene. And also, second, even if the human is erased from the scene, the human might be able to do things in a way that the robot isn't able to do, and so there still might be some domain shift with just how the human is performing actions versus how a robot performs actions. And more importantly, I think the high-level point here is that humans are providing the high-level goals rather than exactly rather than providing exactly how the robot should do the task, the human is just providing intermediate sub-goals of, like, in order to reach this final goal, these are the sorts of things that you should do in order to get there. And I think this is an important point because humans and robots are very different, the human shouldn't necessarily show the robot exactly how to do it. Ideally, the robot would be able to figure out how to actually perform the motor commands to achieve something, but by getting these sorts of sub-goals, the robot can figure out the low-level stuff on its own and get the high-level stuff from a human. And another reference on this point of humans providing high-level goals, that I won't cover it in this lecture, but there was a recent paper by Jacob Andreas et al. On multitask reinforcement learning with policy sketches, where a human provides kind of a sketch of what the robot should do, and it's able to use reinforcement learning to learn from those sketches. Okay, so to conclude with this method, some of the so we pointed out some of the good points of the method, some of the limitations. Again, like we talked about last time, is that the inverse model might ignore important parts of the image because it really only has to predict the action. And it requires an image of the goal for each step, which in some cases might be hard to obtain. And so what if we could, instead of providing an image, give the robot something like language or something that's a bit more natural to provide and a bit more easy to provide? And that's what we'll talk about next. So in this next paper, the authors try to form a method in which the robot can learn from language commands in order to perform a task. And the way that they do this is the goal is to, given some text instruction that, for example, maybe hold the cup of espresso below the hot water node might be an example of a language expression. Maybe something that would come from an instruction book for some sort of machine. And so given this text instruction, as well as a point cloud of what the robot sees, the goal is to be able to figure out the trajectory that performs that task. And the way that they collected data for this and the way that they tried to get humans to provide demonstrations for is they had this online interface where they had an image and they had a segmented point cloud of the object that was being manipulated. For example, in this case, the point cloud, the point cloud of the lever was segmented from the rest of the points. And then there was this arm, this gripper in simulation that the robot manually moved in 3D space and set different waypoints for the arm, for the gripper to reach as the demonstration. Okay, so how would you train the model given some example? So they have the data. They have an example of a point cloud, a text instruction, and a trajectory. So how would you actually train a model to be able to output trajectories given a new text instruction and a new point cloud? So one way you could do it is using behavioral cloning, like we talked about a few lectures ago, where the input to the neural network would be the text instruction and the segmented point cloud, and the output would be the trajectory of how to perform the task. But one of the issues with this is if you're trying to output an entire trajectory, there's actually multiple outputs that actually will succeed at the task. So for example, if you wanted to go put a cup underneath a nozzle, you could first go down and then put it underneath, or you could take a different path to get there. There are many different outputs that will get there, and if you're training a deterministic network to output a trajectory, it's going to have a lot of challenge with dealing with the fact that there's many different outputs that are possible. And the second is that a trajectory isn't just a single action. It's a sequence of actions, and these need to be fairly detailed in that you need to be able to actually get up close to the object and be fairly precise with how you place the object. It's an open loop trajectory rather than being a closed loop feedback system where the robot can actually adapt to its current observation. And this isn't as hard, going back to the model case, this isn't as hard as generating realistic images, but it's still a very hard problem. And so the approach that they take in this paper, instead of just training a policy, is they train a critic model that is given a point cloud, a natural language instruction, and a trajectory, it outputs a score. And the score is just a scalar value that outputs how good that trajectory is for the natural language and the point cloud instruction in the point cloud. And so this deals with the multimodality problem of the trajectories because all it has to do is output a single number and output a single score for the triplet that was passed in. And it can also assign a good score to multiple different trajectories rather than having to output a single trajectory. And then what they do at test time is they search for trajectories using nearest neighbor. So given all of the trajectories in their database, they feed those into the network and find the one with the highest score. And the reason, so they use nearest neighbor and they search through the database of trajectories. The reason why this is valid is that they represent their trajectories in relative to the object. So they shift the coordinate frame of the trajectory to be in the space of the object rather than in the space of the robot. And then this will be able to handle the case where if the robot is in a different position relative to an object that it hasn't seen before, it can just transform into the frame of the object. Yeah. I'll talk about that on the next slide. Cool. So how do you train this? So they pre-trained each, so the input there's 3 inputs to the network, the point cloud, the language instruction, and the trajectory. They pre-trained each kind of encoder of these using an autoencoder. So they, for example, with the point cloud, they trained a network to take an input point cloud and output point cloud and be able to reconstruct the point cloud. And then they threw away the decoder of that autoencoder and initialized the parameters of that encoder using the encoder of the autoencoder. And then the way that they trained it is they for each demonstration trajectory that they got, they assigned a score, manually assigned a score for each demonstration trajectory. And the trajectory that was the most similar to the other, and the way that they did this is that the trajectory that is the most similar to the other trajectories is considered the best trajectory, and the one that is the least similar to the trajectories are scored as negative. So through their interface they collected multiple trajectories for each point cloud and for each point cloud and each natural language instruction, and they said that the ones that are most like each other are the best ones, the ones that a lot of people provided for, and then the ones that are least like those are negatives. And so they then train their network as a binary classification problem between good and bad. Any questions on that? Yeah.
What's the similarity?
They thought about that in the paper, then they defined one in the paper. I don't remember exactly in the details of what they used, but it was definitely something that they considered and something that you have to think about because you're doing a similarity metric between trajectories, which isn't straightforward to define one for. But you can find the details on the paper. Okay. So here's a video of their methods. So for example, the natural language instruction here was to hold the cup underneath the nozzle, and then the robot, here's the robot performing the task. The next language instruction is to press down the lever. And so this is the trajectory that it got as a demonstration that it selected using this method. And you can now see it performing the task. And then here's another example where the language instruction is to turn the switch clockwise. And they actually transferred the trajectory from a different object, in this case a DC power supply. Because it's representing this in terms of the object, it's able to transfer this to the lamp switch. Okay, so this is quite impressive, and it's able to, using these demonstrations, it's able to kind of generalize across objects, which is quite nice. Some of the limitations is that it requires the trajectories to be object-centric. which gets them the assumption that the nearest neighbor queries and trajectories are a reasonable way to get trajectories. And another big limitation here is that it requires that you already have segmentations of the object parts that you're dealing with, which in practice is quite hard to get. There are methods for segmenting point clouds, but generally they're a bit noisy, they have issues, and you also have to figure out which part the natural language instruction is talking about. And second, it requires a large number of demonstrations. So for this paper, they collected 1,200 demonstrations using their crowdsourced interface. And you need enough basically to determine the positives and negatives that I showed on that previous slide. And so you need multiple demonstrations per object and per text command. So any questions on this before I move on to the next method? Yeah.
Did they enforce some kind of sparsity on the joint actions? Because it looked incredibly, like the motion looked incredibly clear in contrast to these wiggly motions you usually see.
Yeah, so what they did here is the demonstrations provided waypoints for the gripper, and then they optimized a trajectory to reach those waypoints. Okay, and so kind of one of the big limitations here is the fact that it requires a lot of demonstrations. And so one question is, can we combine this with reinforcement learning to require fewer demonstrations and have the robot be able to figure out and fill in the gaps from there? And so the next paper that we're going to talk about also uses object-centric demonstrations, like shown before. But it also uses reinforcement learning to try and figure out how to use the demonstrations. And so the motivation actually behind this paper was that they were using this soft hand, which is similar, well, it's an inflatable hand, and so it's controlled by adjusting the pressure in each of the chambers in the hand. And so when you adjusted the pressure, it would move each of the fingers or move part of the hand to actually move the fingers. And kind of the benefits of these soft hands is that you can manipulate fragile things more easily. They're fairly safe to use, and they're also fairly dexterous. So you can, I think with this hand, it can do it can touch each of its fingers with its thumb and do things similar to how humans can control their hands. But some of the challenges is that you can't use traditional control methods with this because you have very poor position sensing and pressure sensing of where actually the fingers are, and there's very noisy actuation of how you actually control the fingers of this hand. And beyond that, it's also difficult to teleoperate, so you can't use kinesthetic teaching with this approach. There's also what's called a data glove, which is you wear a glove that has trackers on each of the fingers and try to collect data with that. But because of the poor position sensing and the actuation, you really can't use a data glove with this hand. And it's not anthropomorphic, which means that it's not quite exactly how the human hand works. And so the motivation here is to use demonstrations, learn from humans in order to learn skills. And like the previous paper, we're going to use object-centric demonstrations because what we care about is the motion of the manipulated objects and not necessarily about exactly how the hand performs the task. And so the demonstrations are going to be given by a human using their own hands. So the overview of the algorithm is that the paper uses guided policy search, GPS, to train controllers. Instead of to imitate a controller optimized with optimal control, it's going to imitate one of these object-centric demonstrations to try and move the object like it was moved in the demonstration. And then train a neural network policy to generalize over individual controllers for different demonstrations. And so here's an overview of the algorithm. It's very similar to guided policy search, where you first collect samples and then fit dynamics. And then at the end, you perform optimal control to minimize the distance to the demonstrations and alternate between supervised learning with the neural network policy. There's an additional step in the middle, which is estimating weights on the demonstrations, because in the method, they provide demonstrations for different conditions, and they want to be able to automatically figure out which demonstration is the one that's most close to the situation that we're in right now. And so here's some of their experiments. So they evaluated on different real-world settings with valve rotation, pushing the beads of this abacus, as well as bottle grasping. And they compared to a few different baselines. And so here's an example of Abhishek providing demonstrations of rotating the valve. And then the robot, for one position, is able, for this position as well as other positions, is able to rotate the valve in the way that was specified. You might wonder what those red shiny lights are. So those are phase space markers, and that's what's being used to track the object during both the demonstration as well as the robot's action. So it can figure out how the object is being moved for learning as well as during test time. And so here's some of the quantitative results that show that it outperforms the prior baseline methods. I'm not going to spend too much time here. And they also showed, so here's Abhishek again providing some demonstrations of how to move the beads on the abacus, and it's able to move the beads to the correct position as specified. Okay, and then the last task was basically grasping this bottle and then picking it up, lifting it up, and using the method is also able to lift it up. And the nice thing about here is that, as you may have noted in the demonstrations, you just saw Abhishek just performing the demonstrations himself rather than actually having to operate the hand of the robot. So some of the benefits of this method is able to learn from a few demonstrations. So using reinforcement learning to learn how to mimic the demonstrations of the trajectories of the objects. One of the limitations is that it does require this phase space system in order to get the object pose. This is similar to the point clouds that were used in the previous task. And this is, I mean, generally in order to get object-centric demonstrations, you need to be able to have the ground truth state of those objects. And with these sorts of approaches, it's less clear how you could make them work from raw pixels or raw observations. Okay, so the last thing I'm going to talk about in terms of domain shift is how we can try to get domain invariance just from raw pixels of watching a human perform the task. So in this last case study, this was a paper that by some folks at Google Brain, and the main idea is that they're going to watch a video of a human performing the task, and they're going to leverage image features that were pre-trained on ImageNet in order to compare the demonstrations to what the robot is doing. And so what they do is they collect demonstration videos of a human performing the task and compute the pre-trained image features on those frames. Then used unsupervised, so they essentially segment the demonstrations into n stages with an unsupervised learning metric just by essentially comparing each of those segments. And they do this for each of the demonstrations independently. I don't have time to go into the details, but that's in the paper. And then they automatically select for each of the segments what are the m most relevant features for each stage. And they do this by looking at essentially the mean invariance of each feature in each demonstration and looking for the ones that have the most similar statistics across the demonstrations for a given stage. And then lastly, once they have the features for each segment of the demonstration, they run reinforcement learning to try and match the features of the demonstrations for the features that were most relevant at each stage. So how does this work? So on the top, here's a video of, so the task that they were considering was having a robot open a door. And so on the top, these are some of the, I think they had 11 demonstration videos of a human using their hand to open the door. And then the robot is trained to try and match the image features that were provided in the human video through reinforcement learning. And this is the final policy that was learned, and it's able to learn how to successfully open the door. Any questions on how this works? Okay. So how does this compare to using the true reward function for this task? So here, the blue line shows a baseline reinforcement learning method that uses the true reward for this task, which is essentially using the reward of how far open is the door. The green line and the red line are showing the method using a video demonstration of the robot arm opening the door, so essentially kinesthetic teaching. And the pink line is showing the videos that I just showed before of using a human demonstration only of a human opening the door, and with the appearance variations of the human hand using their method. And note that all the lines really look about the same, and so it's able to learn with this reward function about as well as just reinforcement learning with the true reward function, which is quite impressive. So some of the benefits of this is that it's very simple and effective, and they're able to learn from raw pixels. And the way that it handles the domain shift is just by using features that were pre-trained from ImageNet that aren't necessarily encoding the differences between a robot hand and a human hand. The limitations is that it's really only as good as the feature, so it does require these features ahead of time, and if the features are classifying between a robot hand and a human hand and are ignoring the door, then it's not going to work very well. And lastly, it really only provides a success-failure classifier. So it only really gives the method some kind of basic information of whether or not the door is open or not, and not actually how the door can become open. For example, how can you, it doesn't provide information of maybe first you want to turn the handle and then open the door. It just provides kind of the classification of whether or not the door is open. And without reasoning about outcomes, it can be harder to try and figure out how to solve the task. And also the agent can potentially fool the classifier by doing something that will get it to say the door is open without actually having the door be open. And so some takeaways from this is that can we reason about the task, and can we reason about these outcomes and how the task can be solved using the demonstrations? And this is akin to what's called inverse reinforcement learning, where we try and reason about the reward and reason about the task from the demonstrations. And I will be talking about inverse reinforcement learning in the next lecture. Okay, and the last thing I'd like to note on this topic of domain shift is we can, in addition to trying to use domain invariant features, we could actually optimize for domain invariance by saying that the features from the human demonstrations should look very similar to the features from the robot demonstrations. And that was done by a very recent paper by Bradley Stady et al. And I won't cover that in this lecture, but you can look at the paper if you're interested in that. So some conclusions. So some ways to try and handle this domain shift when you just get demonstrations from a human and not from kinesthetic teaching or from teleoperation is first thing to try is just to remove the human from the scene. If that's feasible, if that works, that could be a good solution. And have humans provide the high-level goals rather than the low-level execution of the task. Next, you can try and use object-centric demonstrations and only have the demonstration encode things about the object. You can use domain-invariant representations, like the ImageNet features that was used in Pierre's paper, or you can optimize for domain invariance. Okay, so now that we're done with the first topic, we'll take a short 2-minute break, and then we'll talk about safety while learning.
there is somebody who does some kind of bioinformatics in this talk.
You're talking about bioinformatics?
I wonder if there's anyone in the department who's doing any work with that.
There's definitely an area within computer science that does computational biology and bioinformatics. Off the top of my head, I don't know any professor names, but it's definitely an area within computer science.
Yeah, no, I know that. I was just wondering if you knew a professor name off the top of your head.
Oh, not off the top of my head. I could look it up, but
Yeah, well, at that point, so could I.
yeah.
Which is one way to look nice.
Looking at the Mobileye RL paper, they had this safety with policy gradients paper.
I don't remember
It
it.
was a little simplistic, but it was like, I think, for lane changes or something. And they had some very convoluted argument for why policy gradient is not a good idea for that kind of task. This was
When did it come out?
that was like maybe 3-4 months ago.
I don't. I
If
mean,
I'd remembered this yesterday, I would have actually suggested it to you.
Yeah.
To cover. But maybe we can.
I don't remember it. Okay.
No, the thing you said at the end reminded me of this.
Okay, let's get started again. So the next topic is on safety, which matters in many scenarios in reinforcement learning, especially when we're dealing with real hardware. And so the first actually two methods that I'm going to talk about build off of Dagger. So I'm quickly going to recap Dagger, which you learned about in one of the first few lectures, and also implemented in your first homework assignment. So Dagger stands for dataset aggregation, and the way that it works is that we collect some training data from our policy that we're learning instead of using just demonstration data. And the way that we do this is we just run our policy. And so we train an initial policy from the human data that was provided, then run our policy to get a data set of observations, then ask a human to label those observations, label those images, what actions you should take in those images, in those observations, and then aggregate your data set by taking your current data set or your initial data set and the data set that you just collected and repeat. And so, as Sergey mentioned in the earlier lecture, there's one problem with this, which is that asking a human to label these observations is a bit hard to do. It's fairly impractical to maybe go offline and have a human try to label these things or try and it's very hard for a human to provide these sorts of labels. And the second issue is that actually you have to run PyTheta here, which is, and if you're trying to operate a car, if you're trying to learn how to drive, and your policy isn't good at driving yet, then actually running this in the real world and collecting data in the real world is not a good idea, because running PyTheta ultimately you'll probably crash at some point, and it's not safe to just run your on policy your policy to collect more data without any sort of safety constraints. And so how do we deal with these two problems? So there's actually a partial solution to both of these problems at the same time, which is nice, which is that we can train a classifier to classify how good our current policy pi theta is given an observation, for a given observation. And if we're able to accurately predict if our classifier is accurate or not, if our classifier is going to make a good decision for that observation or make a decision that's like our expert, then first we can only request labels for the observations where our policy is inaccurate. So this partially solves the second problem, or the problem on step 3, which is that we can require fewer labels from the human by just asking the human to label observations where our policy is inaccurate. Because where our policy is accurate, we don't necessarily need more supervision information there because our policy knows how to perform the action there. And so this reduces the burden on the human to label a lot of observations. And the second point here, towards getting to the problem at line 2, is that in safety critical applications like driving or other mobile robots, you can switch to a safe policy or an expert policy when the accuracy is below some threshold. Yeah.
What exactly do you mean with accuracy?
Yeah, by accuracy I mean the error between the actions that the policy takes and the action that the expert would take in that state. Yeah. And in practice, what this threshold is going to be something on is the error of my policy between the error between the expert policy and our current policy. Is it below some threshold? Then it's safe. If it's not, then it's not safe. Okay, so this was actually proposed by 2 papers in 2016. And so the first one, actually the one that was second in time, but the first one that we'll talk about, they called this safe dagger. And so the goal was to try and, the ultimate goal was for safety. So it was for having a car being able to drive safely without crashing. And so the way this worked is that, so everything in black here is the original dagger algorithm. So in Dagger, you collect data with a reference policy. Everything in blue is things that were added using their algorithm, Safe Dagger. And so the next step you do is you collect another data set using your reference policy, dsafe, and this data set is going to be used to train the safety classifier. And so then they train a policy using their initial supervised data, and then using only D0, using only the initial data set. And then the safety classifier is trained on both the original data set as well as the data set that was held out for training the original policy, so that it's able to hopefully be able to generalize more and be able to consider scenarios where the learned policy will make mistakes. And then after we train our initial classifier and our initial policy, we then collect data using what they call their safety strategy, which is that if your classifier says that the policy is good and it won't make a mistake, then you use the policy. If your classifier says that your policy is going to make a mistake and it's unsafe, you have the human take over. And then once you train your policy, then you get data. So you basically retrain your policy using the new data that you collected, and you retrain your safety classifier using the data as well. And then you repeat, as in Dagger. Do you have a question?
Yeah, so I guess here, if the human sort of has to be on deck to step in when the policy's not being safe, how is that any better than just him or her labeling the data to start with?
Yeah, so that's kind of a challenge here. It's definitely if the human needs to be on deck like 100% of the time, that's kind of impractical. one way that you could deal with this, I'll mention this a little bit more as a limitation later, but one way that you could deal with it is try and predict into the future whether or not the human's going to be needed. So you can give the human like a little bit of warning rather than having them say, now you need to take over. They don't do that in this paper, but that's one potential solution to the problem.
If you had like some sort of like error bars on the predictions, is there any way to get like useful uncertainty estimates for like things where if you think like maybe like you have like a high uncertainty and like what action you might make that might inform your decision or something for somebody to set in instead of just like the error?
Yeah, so the question was, can you get uncertainty estimates on your policy, and can you use those uncertainty estimates? The short answer is yes, and I'll talk about that in a minute with, so these papers don't actually do that, but there's another paper that does that. There are some issues, and I'll talk about that. Okay, so some results from this paper. So let's start with the left plot here. So the x-axis is showing the number of Dagger iterations, and the y-axis is showing the average number of laps. And I'll start with saying the solid line means there's no traffic, and the dashed line means there is traffic. So the blue line is showing the safe Dagger policy using the safe policy, where the human intervenes whenever the policy is going to make a mistake. And as you would expect, it has perfect performance using the safe policy because the human always intervenes when the policy is going to make a mistake. And the red line shows the performance of the policy that's being learned using safe Dagger. And you can see by the end of training, it's able to successfully complete 3 laps without any human intervention. And then the black line and the pink line show, so the black line shows the performance of just Dagger, and the pink line shows just behavioral cloning. And what you'll note is that it actually is able to learn faster than Dagger is able to learn using this method. Yeah.
So what is safe Dagger naive and safe Dagger safe?
Yeah, so the blue line, safe Dagger safe, is using their safety policy where the human will intervene whenever the policy is going to make a mistake, whereas the red is the policy being learned where the human does not intervene. So the red line is showing actually the performance of the policy being learned. So the red is basically showing that when you, at the end of the training of safe Dagger, it has, your policy has perfect performance on this task. And at the beginning, it isn't able to, doesn't have perfect performance, but this isn't actually the policy that's being used to collect data during training.
I'm sorry, what's the difference between safe Dagger naive and just Dagger naive again?
So safe Dagger naive, safe Dagger naive uses the additional training. Basically, it's being trained using everything in blue.
I see.
So using the safety strategy to collect data, and and then the Dagger naive is not using the blue, so it's not using the safety strategy to collect more data. And then you can also, so the right plot is showing damage per lap. So this is essentially, this was done in a Torx driving simulator. And on the right, you can see that using the safe strategy, the policy doesn't incur any damage because it's accessing the human whenever it wants to. And the red is the naive strategy, and by the end, it's completely safe. And then the other lines show the baselines. Any questions on this? Okay, so the other paper that I mentioned that also proposed this method, the goal wasn't for safety, because they're using a robot arm that was fairly safe and had some safety constraints already built in. But instead, the goal was for efficiency, because if you don't need to ask the human demonstrator to label every single data point, label the actions for everything. You just want the human to label data points that are where your policy is making errors. And so they actually didn't have this safety strategy where they were actually requiring, they had the human jump in. They were only collecting data from the policy that was being learned. And then they had the human label data offline because, so they were collecting the robot samples using the policy, classifying them, in this case using an SVM, and then collecting labels for the examples that were classified as mistakes by the policy. And so kind of the results from this method, so the blue line shows plain dagger on 2 simulated tasks as well as a surgical needle insertion. And the orange lines here show Shiv, the method that uses the classifier. And so the x-axis is showing the states labeled. So basically the amount of labeling effort used by the human, and y is showing performance, where the dotted black line is the level of expert performance. So you can see that using the Shiv method is able to much faster, it's able to reach the performance of the demonstrator using many fewer labels from the humans. Okay, so kind of to conclude with these two methods, the benefits are that you can substantially reduce human intervention and the labeling effort required by humans. And you can also get the safety of the expert while still getting on-policy data, which is beneficial for learning and for learning a better policy. The limitations is that your classifier might fail. So predicting the accuracy isn't easy, and there are scenarios where that your classifier might not be trained on some states that your classifier didn't anticipate that it might think that your policy will be good on. And lastly, intermittent human interventions isn't reliable. It's hard to ask a human to immediately take over given at any given point. So any questions on this before I move to the next method? Okay, and so how can we get rid of that last limitation and ensure safety without reliance on a human to rescue the agent at any given point? And the paper that I'm going to focus on here that I think is able to achieve this is a recent paper on trying to navigate around obstacles by using uncertainty, like I mentioned before, in order to avoid collisions. And so the goal here is to enable the agent to be able to safely learn in a complex a priori known environment. And one thing I'll note is that unlike the previous two methods, this is going to be using reinforcement learning rather than imitation learning. But the kind of the underlying principles can generally be applied in both settings. So the way that this works is they have some data that was collected by the agent, and using that data, we're going to train an uncertainty-aware collision prediction model. So we're going to predict a probability of collision, and I'll talk a little bit more about this model next, but we're going to predict the probability of collision in the future, given future actions that we might take. And the way that we're going to we're going to train this model is it's going to be a deep neural network, and we're going to get uncertainty estimates using bootstrapping and dropout, which I'll talk about in a couple slides. And once we have this uncertainty-aware prediction model, then we're going to form a cost function that's going to be used for reinforcement learning. That's going to be speed dependent and aware of the uncertainty of this collision prediction model. And then using this cost function, we'll gather trajectories using model predictive control. And then these may experience some collisions, and this will be added back to the data set to retrain our collision model to be more accurate. And as the robot becomes more confident, the end goal is going to be able to try and move around obstacles very quickly. And so as the robot becomes more confident that it isn't going to collide, it's going to move more quickly. If it's less confident that it might collide, then it will move more slowly and be safer. Okay, so what is this collision prediction model? So the model looks like this, and it's given the raw image that the robot sees and the commanded velocities or just some actions that the robot is going to take at the current time step and up into the future. We're going to train a neural network to predict the probability of collision h time steps into the future. Okay, and so this is what the cost function is going to look like. We want to move at high speed, so we're going to have the speed multiplier. There's going to be a term on collision. So if we predict collision, then we're going to have a high cost. And if there's large uncertainty, we're also going to have a high cost. And I'll talk how we're actually going to get uncertainty next. Are there any questions on this cost function? Yeah.
So why is the uncertainty an additive term? No. Is there a
Whoops.
reason why it's add? Oh, it's actually. Oh, sorry, I didn't see the brackets. Yeah. Okay. Sorry.
Cool. Yeah.
Don't do like trajectories already code the speed? Like, why would the speed term be?
The speed term is to encourage. So these are predicting collision and large and uncertainty for different speeds. The speed term is that we don't want to collide at high speed, and so this is going to be multiplicative with speed and uncertainty, because if we have uncertainty or if we think we're going to collide, we want to be at low speed. Whereas if we're very confident that we're not going to collide, then we want high speed. Good question. Okay, so this is the cost function that we're going to use with model predictive control. And so how are we going to get uncertainty estimates for our neural network? So there's two methods for doing this in the literature that are the most popular. One is using bootstrapping. And so the way this works is that at training time, we have some data. And the data is going to be split up and resampled into 3 different data sets in this example. It could be more than 3 data sets. And then we're going to train our model using each of those resamples of the data set. And then at test time, we have each of our models. We're going to feed our input into each of those models and take the mean and standard deviation of the outputs of those models in order to get our uncertainty estimate. So the mean is going to be our prediction, and the standard deviation is going to be our estimate of the variance of our model, or our uncertainty of for that input. Does that make sense? Yeah.
So here, I mean, when you use the bootstrap, how many bootstrap networks do you need to actually like store like the weights for?
So I'm not exactly sure how many they used in this method. In practice, one thing that people do is instead of training the entire new network on all of the data, they'll just have each bootstrap be over the final layer of the network or the last few layers of the network, and whereas the top layers of the network will be shared. So then you don't have to store as much, and you don't have to do as much repeated computation at test time when you want to compute these statistics.
Do you think, like, I mean, instead of just bootstrapping it, I don't know if Bayesian neural networks actually are useful, but presumably you would have to just have one network if you were to do variational inference, right?
Yeah.
Uncertainty estimates just like not like calibrated or useful if you were to do that, or?
In practice, these uncertainty measures aren't great. All of them aren't great. But and I'll actually talk. So we actually, in addition to bootstrapping, this paper also uses dropout, which has been shown to be an approximation of Bayesian neural networks. And so the way this works is that at training time, instead of training n different models, you drop out different connections. So in this case, you're randomly dropping out different parts of different connections in the model to get different outputs. And then at test time, unlike normal dropout, so in normal dropout, you train with these dropped out connections by zeroing out these connections. And at test time, you don't include that. But in this case, at test time, you still have these dropped out connections, and you look at the mean and variance across different dropped out versions of your network.
Actually, sorry. So just to process, I mean, one thing that's a little bit weird. I mean, so I know Yarn, like you have a specific dropout probability you have to put in the network when you do test time, right?
Yeah.
So that'll definitely affect like your sigma, right? So do you just tune that to get a sigma that works? Because the bootstrap and all those other things, it's like you can argue it's like slightly more principled because you just bootstrap a bunch of networks.
Yeah.
And there's no like free parameters. So do you just tune the dropout probability to get like a sigma that works for the problem?
I believe so, yeah. And so actually in this method, they used both dropout and bootstrapping in the same network because they found that neither of them worked well enough on their own, but using both of them was able to get some reasonable uncertainty estimates. All right, so any questions before I get to results? Yeah. So dropout is done at test time such that, so our goal is to get the mean invariance of the output. And so at training time, if at test time we remove the dropout, we would just have a deterministic network. And so here we want to drop out, we want to kind of estimate the probability of estimate the variance of our output. And if we drop out different connections at test time, then we'll get different outputs from the network. And there's a lot of theory from Yarngal and Zubin on how this is approximating Bayesian neural networks, where you have basically some prior on your weights being having some mean invariance, and you're trying to estimate the uncertainty of the entire model.
So
Yeah.
this entire model is includes the states or just measurement?
Sorry, what?
So you mean the estimate your entire uncertainty?
Yeah, uncertainty, the uncertainty of the output of the model.
Not the state.
Not the state, no. And this is the model that is outputting the prediction of the probability of collision given the initial observation and the future actions. Okay, so how well does this work? So Greg had 2 experiments in this setting. One was a car, and the goal was to move as fast as possible while avoiding obstacles, either the cone or obstacles on the side. And so Greg had different trajectories that the robot could take. In this case, he just hand-coded these sorts of primitives that the robot could choose. And then the initial random policy had a lot of collisions, as you can see here. And then during training, it slowly learns to avoid collisions. And when making collisions, it avoids making those collisions at high speeds. And the final policy is able to very quickly maneuver around the obstacle. And so this plot is showing, on the x-axis it's showing speed, and on the y-axis it's showing the number of crashes. And so generally we want our crashes to be at lower speed, not at high speed. The right is showing the method that I talked about here, and the left is just showing without uncertainty, without these, without this model of whether or not we're going to collide. And you can see that using the uncertainty estimates, it's able to move its collisions to lower speed rather than to high speed. And so this is a rollout of the final policy. And you can see it kind of cuts the corner, but it's able to avoid collision. The second experimental domain was using a quadrotor that was trying to fly around an obstacle. And so in this setting, safety is more important than the car because the quadrotor is less fragile. And so on the left, you can see that if you collide at high speed, the quadrotor crashes and actually breaks and falls. Whereas if the quadrotor goes at a lower speed and collides, it's able to just bounce off and maintain its current position. Okay, so on the left is showing the method without uncertainty estimates, and on the right is showing the method that I described with uncertainty estimates. And you can see over time, the method on the right is more cautious, and it learns how to slow down when it's going to collide and crashes much less often as a result. And at the end, it's able to learn how to get around the obstacle. And you can see the plot on the top, plotting, again, the number of collisions, the speed versus the number of collisions. And you can see without the uncertainty estimates, it collides very, very frequently at high speed, which obviously isn't good for the quadrotor. Okay, and then the final policy so here are the final plots, and the final policy learned by the quadcopter is able to successfully move around the obstacle. Okay, so to conclude this section, I think the benefits and limitations, so the big benefit of this method is that it's able to take into account uncertainty of collision, which is very important because you don't just want to estimate whether or not you're going to collide, you want to also be able to figure out, you also want to reason about whether or not how uncertain you are about colliding. And another benefit is there's no reliance on a human to take control. So this operates under the assumption that if you slow down, you're going to be safer. And so therefore, if you think that you're going to be unsafe, then you should slow down and continue learning. One of the limitations is that in some scenarios, slowing down might not always be a safe option. In practice, I think it's a fairly wide-reaching assumption. But if you're, for example, driving on a highway, you might not want to slow down if you're uncertain about getting into an unsafe scenario. Then again, it isn't necessarily, slowing down might be the correct action to take. And the second limitation is getting good uncertainty estimates is hard. So in this scenario, we use bootstrapping and dropout to get uncertainty estimates. But in practice, I think this is still an open problem in how we can get these sorts of uncertainty estimates from neural networks. So some conclusions to learn safety, we can use data from a safe policy, off policy in order to learn and also account for uncertainty and be cautious in high-risk situations. And as I just mentioned, so kind of an open challenge is being able to predict safety into the future and reason about the model's uncertainty when you're making these sorts of predictions. Okay, so that's the last part of that on safety. I'm going to quickly go through improving imitation with learning with experts. I don't have a ton of time, but so I'll go through this a bit quickly. I apologize, but hopefully it will make sense. So actually, any questions on this on the safety portion before I move on? Okay. So this last section is on imitation learning from experts, which we covered earlier in the lecture. And in particular, I'm going to talk about 2 improvements on guided policy search. As you might recall, the way that guided policy search works is that we're going to try and learn this neural network policy by training it to, with supervised learning, to mimic these local controllers, these local trajectory-centric controllers. And so we're going to minimize our cost function of our trajectory such that our policy matches those trajectories, matches those local controllers. And so the way this works as an algorithm is that we're going to use ILQR to find the trajectories, use stochastic gradient descent to train the neural network to match those trajectories, and then update the dual variables. Okay. And so a second recap, this method is going to kind of take some motivation from policy gradient as well. So using policy gradient methods, we try to update the parameters of our network using this equation. So we have our the likelihood ratio term as well as our baseline, which is going to reduce variance. And the way this is going to work is that we're going to try and, unlike policy gradient, which optimizes in parameter space, we're going to try and do the optimization in policy space. And so what do I mean? So your parameters are theta of your policy, and say this is your parameter space theta. In this case, it's just 2D for visualization purposes, but in practice, it's much higher dimensional. And so in parameter space, your optimization might look like this, where red is good and blue is bad. And whereas in policy space, your parameters are going to project somewhere in policy space, and you might take a different path to get to the optimum. But in practice, our optimization surface isn't going to look like this nice Gaussian blob and this very nice convex surface. It might have a lot of local minimum. And so in parameter space, especially in parameter space where you have a lot of high dimensions, and you might not reach the global optimum when you try to optimize. Whereas in policy space, trying to optimize for the policy in practice might be a bit easier because you might be able to find the kind of the policy. If you're using it, you're trying to use trajectories and trying to make these updates using trajectories, you might be able to find the local optimum, find the optimum in this policy space, and then project it back to what your policy can represent. And so why policy space? The local optima might be less of a problem, and the optimization landscape is probably going to be a bit easier. And so it can be easier to update make an update in policy space rather than parameter space. So what does this look like as an algorithm? So kind of what mirror descent looks like as a method is you optimize your function without worrying about the constraints of, optimize your cost function without worrying about the constraints of your function. And then you project it back onto the function space that you're learning, or your policy, or in the reinforcement learning setting, your policy. And so in reinforcement learning, what this looks like is our objective is to minimize cost. And so the first step we're going to do is we're going to try to optimize our policy such that we're within a KL constraint of our old policy. And then we're going to project that policy back onto the space in which our parameters can represent. The projection is done just with supervised learning. And the local policy optimization can be done with the trajectory-centric model-based RL or with path integrals, which I won't cover today. Furthermore, one of the limitations that we mentioned before with GDPS is that it requires random deterministic resets in order to train a local linear model. And one way that we can get over that assumption is if we have some random initial states like here, we can actually cluster those initial states and then fit our trajectory distributions to those initial states and fit our local models within those clusters. So for each of these clusters, we're going to fit our time-varying linear dynamics to each of those clusters and update each of our controllers for each cluster, and then use supervised learning to match all of the clusters. And so there's some real-world experiments with this method. This method is very comparable to the assumptions that reinforcement learning methods make. And so you can see on the right, these are graphs. These are learning curves of the number of samples versus the cost. And you can see the red, blue, and black are showing guided policy search-based methods, whereas the pastel colors are showing policy gradient methods and TRPO. And you can see that they're orders of, so this is a log scale on the x-axis, and they're orders of magnitude more efficient in the number of samples that they're able to use. So for example, this simple 2D reaching benchmark, TRPO can get to the goal using around 3,000 trials. DDPG and NAF can use around 2,000 trials, as well as QProp, which is a new RL-based algorithm. Whereas using mirror descent guided policy search is able to use around 500 trials for these tasks. Okay, I know that was fast, but we're out of time. Some conclusions is that optimization in policy space can be easier than in parameter space. And using clustering for learning local linear models for random initial states where you can't deterministically reset in the environment. And next time I'll cover inverse reinforcement learning. So I'll see you on Wednesday.